All right, everybody, you know who it is. We're back. We're back with another video of how to do an astro problem, a how-to guide, if you will. I will say I've started to see some funny memes come out of these videos, so definitely keep those coming, and I'll keep the videos coming. Let's begin. All right, today we're going to talk about Hohmann transfers, and if there's any problem across the entire course that lends itself really well to kind of a recipe process to help you understand the relationships, it's this. Truly, Hohmann transfers are almost set up for this. So I want you to learn the process, as always, but I also want you to understand the relationship, and this is going to be a source of free points for you on the GR. So with that, let's take an example problem as we do. An example problem that I have today, it says the following. It says, it's an old Hohmann problem. It says a satellite will transfer from a parking orbit that has an altitude of 500 kilometers to a mission orbit of an altitude of 1,800 kilometers. So we have a little bit of vocabulary that we should go over. Satellites get launched generally into what we call a parking orbit. So this is an orbit where the satellite is not ready to begin its operations yet. It's being checked out and tested by engineers and operators before it's finally handed over to the government to operate as a weapon system. So when you launch into a parking orbit, it's basically an orbit literally where the satellite is parked, although it's still moving. It's just going to remain in this orbit until it's finally ready to go out to the final mission orbit. The mission orbit is the final orbit that the satellite's going to stay in throughout its life and conduct its mission, whether it's communications or, in the case of GPS, navigation, right? Whatever the mission is, the mission orbit is the orbit from which the satellite's going to do. Yeah, it's going to do the mission. Okay, so second vocab thing we need to have a heads up for, and this is tricky, don't be tricked. It says the initial orbit has an altitude of 500 kilometers. I think a picture may be worth at least a few words, maybe not 1,000, but drawing a picture is going to help here. So first of all, maybe I have my Earth here, right? I have the initial orbit here. I have the final orbit out here. I want to make sure I label. I'm going to call this my orbit number 1 here. Oops. Yeah. And then call this orbit number 2 out here, just so I know where I'm going. And starting off in this 500 kilometer mission orbit, so the radius here, that's the radius of the Earth. Oh, very tiny. R sub Earth symbol. And then if I add the altitude that the satellite is at, and of course this altitude is 500 kilometers, this altitude, that altitude is 1,800 kilometers. I still have to add in the radius of the Earth for both of those to get the semi-major axis. So what I'm going to do is I'm going to label everything having to do with orbit 1 with a little 1, everything having to do with orbit 2 with a little 2. So first things first, I want to find the semi-major axis of my smaller orbit, orbit number 1. So what I have to do here is add radius of the Earth to the altitude that we're given. That is going to provide a value of, I think I could even do that in my head, 78.137. Let's do the same thing for the semi-major axis of the second orbit, which is also circular. We're told that they're both circular orbits. So to start this off, for this entire problem, and this is the simpler case, where we're going from an initial circular orbit to a final circular orbit. There are possibilities. I've seen homeworks and tests and such in the past where you're going from an elliptical orbit to a circular orbit. So I'll try and point out where the changes would be, but for this initial problem, to help you understand the concept, we're going to assume the simpler case, which is a circular orbit going to another circular orbit. Okay, cool. All right, so anyway, let me resume with finding the semi-major axis here of my second circular orbit, the bigger orbit, the mission orbit. This one, I'm not going to rely on my flaky brain. Oop. Gives us 81. 71, 78. All right, so for this, we finally get to use some equations that we've been kind of dancing around since the beginning of the course, but haven't really used yet. And so over here you see, over here under two-body equation of motion again, we have V equals this mess. That's for elliptical orbits. So I might even write V elliptical for myself. And then you have a V circular orbit, which is labeled. And so here's what we want to do. The general process is this. We want to find the velocity that the satellite is in when it's in orbit number 1, when it's just happily beeping and booping. Boop, 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 boop. We want to find the velocity that's right after the burn. And for my picture, I'm going to say that the burn occurs right here. The satellite fires its little thrusters right here, and that puts it into a transfer orbit. See if I can draw a dotted line. What I'm going to do is highlight that. So that you can kind of watch or see the track of it. So it'll start here. And it'll go to its final mission orbit, which I'm also going to highlight. Just for the heck of it, may as well highlight the beginning orbit, the mission orbit. Okay, so now maybe the colors will help us pick out what's going on. So I'm going to find the velocity in the blue orbit, the initial orbit, the parking orbit, right? We have lots of names for it. And then satellite's going to fire its little thrusters right here. Then it's going to enter this pink transfer orbit, which you'll notice, which is highlighted by the fact that I can't draw dotted lines very well. It's a highly elliptical, very elliptical orbit, right, to go from orbit 1, blue orbit, to the final mission orbit, which is the yellow or green orbit. Looks like it shows up yellow on the screen. So, okay, so I want to find those velocities, and I'll show you how to do that. Then we're going to find the velocity of orbit number 2, how fast the satellite's going to go when it finally hits this mission orbit. And you know what? I'm going to adjust this. We'll find the velocity right before it fires its thruster, and then the final mission orbit. So let me just label some things. When the satellite's just in the parking orbit, it's going a velocity of v sub 1. Right here, after it fires its thruster, it's going v sub transfer 1 because it's entered the transfer orbit by firing its little thrusters. And so I label it v sub t1. That's supposed to be a little cursive t. And then it travels in this parking orbit, sometimes for several hours. And then right before it fires its thruster here, it's going vt2. And then when it's finally happily out here in its mission orbit, beeping and booping, it'll be going just v2. Okay, so let's begin. The question says, first of all, draw the transfer orbit and label where the burns will occur. Well, I label where the first burn is going to occur. First burn occurs right here at the blue orbit. The second burn occurs right here, finally out the yellow mission orbit. So we've done that. We've labeled the orbits and where they'll occur. The question says, okay, what's delta V1? Which means what's the burn? What's the change in velocity from V1, where it's in its parking orbit, to right shortly after it's burned its first burn, like fired its thrusters the first time? The way we could write that mathematically is whatever the difference between v sub t1 is, like the transfer orbit velocity right here, and v1. Notice I put an absolute value because we're trying to calculate essentially fuel costs, fuel amounts. And so we need to know how much gas to put in our either our second stage booster or our satellite, however the satellite's set up. So delta V1 is the absolute value difference between V sub transfer 1 and its original mission, or sorry, wrong, original parking orbit. Okay, so let's find V1. Would you guys buy, hopefully, that V1 is a circular orbit? I would. So we're going to use this equation here. V sub circ equals mu over r. Well, which r? So this is where you start to make your money really here, is to keep track of which r is which and which a is which. So R1, would you buy that for a circular orbit, the radius is the same as the semi-major axis? I would recommend that. So, excuse me. So what we could label is R1 is the same as semi-major axis 1. R2 is the same as semi-major axis 2. So that gives us the numbers that we can use to plug and chug here. R1 we found to be 6878.137. Alrighty. I get 7.613 kilometers per second. Remember units. Okay, and so now we want to find the velocity right after the satellite fires its thruster. And of course, it's still going to be right here in its R1 orbit, right? Its first orbit, its parking orbit. And the equation sheet tells us that's the square root of 2 times mu over r. Oop, there we go. Plus epsilon. Okay, so which r? Well, we know that it fires its thruster, bang, instantaneously. And it's still at its parking orbit. So we're going to use R1 here. But epsilon, you guys might remember, is specific mechanical energy, and it's equal to mu over 2a. Which a? I'm going to tell you. It's a secret a, if you will. It's actually the semi-major axis of the transfer orbit. And so the semi-major axis of the transfer orbit we need to find. I didn't write it up here because it wasn't time yet. But semi-major axis of the transfer orbit is the semi-major axis of both the initial orbit and the final orbit. Nope. Don't forget that. 81, 78, 7. All over 2. You just divide it by 2. You average them if you want to think about it like that. Let's see here. Oh, no. And that gives us a semi-major axis for the transfer orbit of 7528.137. Again, all these are kilometers. I'm running out of space in my drawing, but you can see it there. Okay, so that's what this mu is here this is what this epsilon, the specific mechanical energy is. So if I were to write it in full here, I'll write it 2 mu over R1 minus mu over 2 times semi-major axis of the transfer orbit. And math-wise, let's do the thing we do. We plug and we also chug. Cool, there's mu. R1 we found was 6878.137. Now we'll plug in mu here, and then 2 times, I'm running out of space, 2 times 75, 28.137. Let's see what that comes out to be. Okay. So that will give us a VT1 of no, it's the wrong button. gives us 28, almost 29 within this, and then we're going to take the square root of that. Okay. So right after we fire our thruster, oh, disregard. Gives us a, so after plugging and also chugging, get that to be equal to 7.934 kilometers per second. All right, so now we know how fast the satellite was going in its initial orbit, 7.613. And then right after it fired its thrusters to get into the transfer orbit, the pink orbit, which as you can see is only half an orbit. We'll talk about that in a second. But to fire, it gets into this transfer orbit, and then it's going 7.934 kilometers right here, right before it, or right as it enters the pink orbit. So the difference in those two, again, is velocity right after we fire the thrusters minus our initial velocity, absolute value. Oh, don't forget. Okay. And I get the delta V, the first burn, to be 0.321 kilometers per second. Okay, that's what the problem wanted. Now, the problem's also going to want, and it does, what's the delta V2 for the second burn? Well, this process is going to look very similar. So this is kind of be our step 2 here. So imagine with me, if you will, now the satellite has spent all this time in this pink transfer orbit as it goes across, and it's finally ready to do its second burn. It has to do 2 burns, remember. It has to do a burn to get out of the initial orbit and a burn to enter the mission orbit, the final orbit. So right here, before it fires its thrusters at VT2, let's find that first. And just for context's sake, let me write this. We're going to find delta V2 the same way we found delta V1. This absolute value of the transfer orbit, the second burn, minus the velocity at the mission final orbit. All right, so we'll come back to that. Let's find VT2. We're going to use that same equation that we used to find VT1. We're just going to plug in different values. So now what changes and what doesn't change? Well, that's where you make your money with this, is learning and remembering what changes. So remember VT1, we were still right here in our initial parking orbit. So we used R1 here. Well, when we get out all the way to our mission orbit, right as we do our second burn, we're at the mission orbit. So we're going to say R2 here. And what doesn't change is epsilon. You're still going to use negative mu over 2 times A of the transfer orbit. So now let's plug and chug. From above, we got that the radius of the second orbit, which is to say the center major axis of it, is 8178.137. Great. And that'll be minus 398600.5, which is mu over 2 times, again, center major axis of the transfer orbit, which is 7528.137. Now let's plug and chug. See what VT2 gives us. Okay. And I get 6.673 kilometers per second. That makes sense. I'll tell you why in a second. Let's find our final mission orbit. This is going to be the very same way we found V1, the velocity at our parking orbit. We're just going to use R2, the radius of our mission orbit. This is 6.981 kilometers per second. All right, and now we're at the point where we can finally find the second burn, the size of that delta V. You remember it's the velocity right before we fire the thruster minus the velocity right after we fire the thruster. Let's see here. I get that to be about 0.308 kilometers per second. We're almost at our final step here. The total delta V, which is to say the entire tank of, or the entire, what would you say? I suppose the entire fuel load that you're going to need to go from orbit number 1 to orbit number 2 is the size of delta V1 plus delta V2. So what was delta V1? We found it was 0.321. We found delta V2 was 0.308. That gives us 0.629 kilometers per second. That's the delta V of a Hohmann transfer. That's the most energy efficient way to get from orbit number 1, the blue orbit, to the yellow greenish orbit, which is the mission orbit. That's almost the end of the story. Almost. The last thing the problem wants is a time of flight. So this is somewhat similar to the time of flight we found in the orbit prediction lesson, last lesson, but we're going to find it in a much, much simpler way. So we know that the period of an orbit from the equation sheet is 2 pi times a cubed over mu. The question is which a? Well, the time of flight is the time it takes for the satellite to do a burn here instantly, right? And then spend time in the pink orbit getting out to the mission orbit. So basically all the time that it spends in this half elliptical orbit is the time of flight. So the semi-major axis we're going to use is the semi-major axis of the transfer orbit, which we found to be 7528.137. And we'll go ahead and cube that all over 398600.5. And when I do the math, I get it's 6,500 seconds, a little left over. But you see this period equation from the equation sheet that we used, it gives us the time that the satellite would spend if it spent an entire orbit in the transfer orbit. Like if it went, in this pink path and then continued around elliptically, That's what the period equation gives us. That's not how much time it spends only in the pink part of the orbit. So time of flight really is the period over 2, because it only spends time in the pink part of the orbit. And that gives us a pretty even 3250.216 seconds. And you can just usually leave it like that if the problem doesn't say you need it in hours, but since I'm used to it, I like to convert that to an amount of hours. And it clocks in at about 0.903 hours, so almost just shy of an hour. So let's take a look at this example Hohmann transfer that I cooked up. So let's say this little satellite is happily in its parking orbit, but it wants to transfer out to a much bigger mission orbit. It does this first burn right there, and now it's in this very long elliptical orbit, and it can spend a long time in this elliptical orbit, especially if it's going out to geostationary. But right about the time it's ready to enter its final mission orbit, it does a second burn, and it places it into this pink mission orbit. That's the color that I used there. So at that point, you've done your Hohmann transfer, and you did the most energy efficient method to get your satellite all the way out to its mission orbit.